We are going to talk about p-values, an important statistics concept, in 3 minutes. In the 1930s, mathematician Ronald Fisher had a colleague who claimed that she could detect when tea was poured before milk. Intrigued by the claim, he made an experiment on the spot. He made 8 cups of tea. 4 had the milk poured first, the other 4 had the tea poured first. He asked her to identify which was which. Remarkably, she got them all correct. This begs the question, what is the probability she was guessing by random chance? And still got the correct answer. Without deep diving into the permutations and combination math, the answer is 1 in 70, or about 1.4%. Now ask yourself this, is that likely enough to be a coincidence? 1.4% probability? Because that probability is so low, so unlikely, the p-value, we are inclined to think she has a special ability, and she wasn't randomly guessing. More formally, we will call the status quo, where we assume she's randomly guessing, to be our null hypothesis, H0. And that is going to be any p-value greater than or equal to 0.05, if that's going to be our threshold. But if that p-value is less than 0.05, we entertain the alternative hypothesis, H1, that she has a talent. We can therefore reject the null hypothesis that she was guessing. We can then promote the alternative hypothesis. But what about predicting a continuous value, such as a mean that comes from a sample, and we're comparing it to a population? Let's say a cold takes 18 days to recover on average, with 1.5 standard deviations as reflected on this bell curve. This normal distribution has an area of 1.0 under it, and we take fractions of that area to find the probability for given ranges. Let's set a p-value threshold of 0.05, leaving only 0.95 area remaining in the middle. Let's say we test out a new drug on a statistically significant sample size of 31 or more patients. They recovered from the cold in 16 days. Did the drug have any effect? Recall that it takes 18 days on average to recover from a cold. This is going to be our null hypothesis. Our alternative hypothesis is that the mean is no longer 18 because the drug did something, whether it decreased or increased the duration of a cold. This is what we call a two-tailed test. Intuitively, we can say that because the drug average recovery time was observed inside this 0.95 area, we fail to reject the null hypothesis. We can't say the drug is having any effect. Let's try a different drug. This one has an average of 14.9 days of recovery. Because it is outside that 0.95 area, we can say this is unlikely to have happened by random chance. Perhaps the drug is doing something, given our 0.05 threshold. But what about the p-value itself? How do we calculate that? So the p-value is going to be anything equal or less likely to the outcome we observed. So 14.9 or less days, what is that area? That is 0.0194. But we are capturing equal or less likely outcomes. We have to capture the symmetrical probability on the other side where the drug could have extended the cold. After all, our null hypothesis is the mean is 18, and our alternative hypothesis, the mean is not 18. It goes both directions. Doubling that area gives us our p-value of 0.0388. Because that is less than 0.05, we reject the null hypothesis and promote the alternative hypothesis that the mean is no longer 18. To support this channel, please go to the link in the description. O'Reilly.com has my books, live online trainings, and courses. You also get access to an enormous library of content from various publishers. You can get a 10-day free access by following the link below. Thank you very much. I will see you next time.